operator, unitary operator and normal operator both. Actually today's goal of this lecture, today I will see unitary operator, because in my previous video I had seen briefly self-adjoint operator and normal operator. Today I will see unitary operator actually, because this is today's goal of this lecture. At first just recall what is the self-adjoint and normal operator. We all of us know, in my previous video I had discussed this part briefly. Let T be a bounded linear operator who is mapped from S to S, where A is be a Hilbert space. And the operator T on this Hilbert space is self-adjoint if T star equal to T. That means inner product Txy equal to, this is equal to inner product x comma T star T adjoint y, and we all of us know adjoint of T is equal to T when T is self-adjoint. This is equal to inner product x Ty, and the operator T on A is unitary if and only if T star T, that means T star T equal to T star equal to identity. That means in a previous video I had seen, in normal operator both operator and adjoint are commute, but here also this value is identity. When T star T equal to T star equal to identity, then the normal operator is said unitary operator, where I is mapping from S to S, which is identity operator. I hope my all viewers have understood what is self-adjoint operator, what is unitary operator and what is normal operator. Okay. In self-adjoint operator, T is equal to its adjoint, and in normal operator, the operator T and its adjoint always commute, and in unitary operator this value, in unitary operator this value is equal to always identity. Okay. Let's see some properties of unitary operator, because today's goal actually about the unitary operator. First remark is an unitary operator always be bisective, because when T be a bounded linear operator which is unitary operator, if consider 2 point xy belongs to A such that consider Tx equal to Ty. Now multiply both sides by T star, then T star Tx equal to T star Ty, and since T be unitary operator, that means T star T equal to identity, that imply x equal to y. That means that imply, since from Tx equal to Ty imply x equal to y, that imply T is 1 1. And T is also on 2 because consider one arbitrary vector y belongs to S. As the adjoint operator T star is from S to S, there exists x which is equal to T star y which belongs to S. Then multiply this equation by T, then Tx equal to T star y, and T star means, since T is a unitary operator, T star means identity which is equal to y. Since I have got Tx equal to y, so obviously T is on 2, because here this is true for any arbitrary y. That means for unitary operator T is always bisective operator, and in unitary operator are those operator whose Hilbert adjoint operator means T star is same as their inverse. That means T star is same as T inverse. Okay. Next, let T be a bounded operator which is unitary operator. Then obviously I have got, when unitary operator, that means T is bisective, and now we have to prove In unitary operator which is bijective, then adjoint operator is actually its inverse. This is because since T is bijective, that means T inverse exists. As T star equal to identity, because this is unitary operator, now multiply both sides by T inverse. Then that implies T inverse time T star equal to T inverse identity. And by the associative property, this implies the T inverse T star equal to T inverse. And T inverse T means actually identity, that imply T star equal to T inverse. That means adjoint operator is equal to its inverse when T is unitary bounded operator. Okay? That means for unitary bounded operator, its adjoint is same as its inverse. So, unitary operator always bijective. So, for unitary operator, inner product Txy equal to x comma T star y, and obviously T star y means T inverse x comma T inverse y. Okay, this is for unitary operator. That means in unitary operator, adjoint is always same as inverse. Now I will see unitary operator is normal, but normal does not mean unitary. Since here T star T equal to T star equal to identity, see, so obviously for this value this is obviously be normal, but when the operator is normal, this does not always imply this is unitary. Now consider one example which is normal but not unitary. Consider T equal to 2I identity, which map from Hilbert space to Hilbert space, and identity map from Hilbert space to Hilbert space. It can easily seen T is 2II, because this is multiple of identity operator always be linear and bounded, and this is multiple of one scalar, so obviously this is linear. And T star equal to 2I identity, that means T star equal to 2I bar identity bar. That means this is equal to minus 2I identity. Notice here T star equal to minus 2I identity and T equal to 2I. Therefore, T not equal to T star. So, T is not self-adjoint. Also notice T star equal to 2I identity minus 2I identity. This is equal to minus 4I square identity whole square, identity square. This is equal to 4I. And T star T equal to, this is means minus 2I identity times 2I identity. This is also equal to minus 4I square identity whole square. This is also equal to 4I. Notice here T star equal to T star T. So obviously that implies T is normal. But this is not equal to T star equal to T star T not equal to identity. So T is not unitary. So this example shows normal does not always imply unitary. But unitary, this imply always be normal. Now I will say some properties of unitary operator. Let T be operator on S, then following condition are equivalent. 1. T star T equal to identity. Second, inner product Tx Ty equal to inner product xy for all xy belongs to H. Third, norm Tx equal to norm x for all x belongs to H. First, suppose T star T equal to identity operator. Then, inner product Tx comma Ty, we can write this as x times T star Ty and T star T equal to identity. So, this is equal to x comma, this is equal to identity times y, this is equal to xy. And this is true for x, y belongs to Hilbert space. That means inner product Tx Ty equal to inner product xy. That means here in unitary operator, inner product preserved. Also, similarly, norm preserved. In unitary operator, norm preserved, distance preserved, metric space preserved. Next, I will see third. From second, I have got inner product Tx Ty equal to inner product xy. And this is true for all xy belongs to S. Now, replace y by x. Then, inner product Tx comma Tx, this is equal to inner product x comma x. That imply norm Tx whole square equal to norm xl whole square. That means norm Tx equal to norm x. So, in unitary operator, or inner product, norm, all are preserved. Similarly, distance are preserved. So, in finite dimensional inner product space over the field F, a linear operator T on the vector space V is said to be unitary if the field equal to complex number and norm Tx equal to norm x. This is true for all V belongs to V. And this is true in finite dimensional inner product space. And the field, when the field is complex number, and when the field is real number, then T on the vector space V is said to be orthogonal if norm Tx equal to norm x, and this is true for all x belongs to V. That means, so if V be a finite dimensional inner product space, then T is unitary if and only if T preserves the inner product space. That means inner product Tx Ty equal to inner product xy, and this is true for all xy belongs to the vector space V. And for infinite dimensional vector space, if V an inner product space, then T be an operator on the vector space V, then T is unitary if and only if T star T equal to T star equal to identity operator. That means in finite dimensional inner product space, when inner product preserved, then we can tell the operator T is unitary operator. But in infinite dimensional inner product space, when T star T equal to T star equal to identity, then this operator is called unitary operator. Okay? OL. Next few result of unitary operator, let S and T, two operator are unitary on the Hilbert space S. Then I have proved few minutes ago T is isometric. Actually, when finite dimensional, then inner product preserved, and when infinite dimensional, then since always the inner product preserved, so T is isometric. Norm T equal to 1 and ST. If S and T unitary operator, then their product also unitary. And T inverse equal to actually T star, which is also unitary. Norm T means actually supremum norm Tx where x belongs to H and norm x equal to 1. And norm Tx means actually since inner product norm all preserve unitary operator, so this means actually norm x. where x belongs to A such that norm x equal to 1. That means from this value is 1. Therefore, in unitary operator norm T, this value is 1. Now I will see ST also unitary operator. Why this is true? ST star ST means by the property of adjoint, this value is T star S star times ST. Since given S is unitary, that means S star S equal to identity. So this value is identity. So this means T star T, and T star T is, since T is also unitary, so this value is unitary. Similarly, ST star, this value is equal to ST T star S, and since T is unitary, so this value is equal to identity. That means this is equal to, T star S star also. This is equal to S star, which is equal to identity. That means I have got ST star ST equal to ST star, which is equal to identity. So that implies ST is unitary. And we all of us know, few minutes ago I have seen T star equal to actually adjoint operator, and this is unitary. Okay, this is the all properties of unitary operator. So if T be a unitary operator over the vector space V, where V be a finite dimensional vector space, then the matrix of T denoted by A relative to every orthonormal basis which satisfies A star A equal to A star equal to identity. That means if T be a unitary operator where over the V, where V is a finite dimensional vector space, then the matrix with respect to orthonormal basis, this matrix is A, is said to be unitary if A star A equal to A star equal to identity. And if A is Cn cross Cn, is called unitary if A star A equal to identity. That means a matrix is said to be unitary if A star A equal to identity. Also in for real, this is called orthogonal if A transpose A equal to identity. The converse also hold. That means with respect to orthonormal basis, if the matrix is unitary, then the operator obviously unitary operator. Converse also hold. And we all of us know there are various property of unitary matrix. This property we all of us know this property. Just as a recall, A is n cross n matrix, then following are equivalent. A is unitary. Second, A is non-singular and A star equal to A inverse. Third, A star equal to identity. Fourth, A star is unitary. Fifth, the column of A are from orthonormal set. Similarly, the rows of A from an orthonormal set. But the column of A from an orthonormal set, because if A equal to the vector u1, u2 up to un, then A star A means u1 star, u2 star up to un star, here u1, u2, un, and this is equal to u1 star u1, u1 star u2 up to u1 star un. Here u2 star u1, u2 star u2, so on u2 star un. This would be continue. This is un star un, u1, un star u2 up to un star un. and this is equal to, since A star A equal to identity, this is means 1 0 0 0 1 0 up to 0, and this would be continuous 0 0 0 1. That imply U1 star U1 equal to 1, U1 star U2 equal to 0. So U1 star UN equal to 0. Similarly, U2 star U2 would be 1, UN star UN would be 1, other value would be 0. So that means actually UI star Uj would be delta Ij when, and this value is 1 when I equal to j. Otherwise this value is 0 when I not equal to j. That means the column of A forms an orthonormal set. Similarly, the rows of A from an orthonormal set. I hope my all viewers have understood the all properties of unitary operator. Okay? OL. Next property, if A is unitary, then absolute value of determinant is 1, and if modulus of determinant is 1, then that implies determinant of the matrix is either plus minus 1 or plus minus I, and this is because since A is unitary, that means A star A equal to identity. If we apply det with both sides, then this would be who is equal to 1, and this means determinant of A star times determinant of A, which is equal to 1. And we all of us know, and determinant of A star means actually determinant of A conjugate transpose, and actually determinant of A transpose is same as determinant of A, then that means this is equal to determinant of A conjugate, and determinant of A conjugate is equal to determinant of A conjugate whole bar. So that implies, this means from these lines determinant of A conjugate, determinant of A whole conjugate times determinant of A equal to 1. That imply absolute value of det A whole square equal to 1. That imply determinant of the matrix A is equal to plus minus 1 or plus minus I. I hope my all viewers have understood this is clearly. Okay? Well, that means for unitary matrix, determinant always plus minus 1 or plus minus I. When real field, then determinant always plus minus 1. Today I have stopped here, but I will highly recommend you please see today's video, unitary operator and properties of unitary operator. Please see this topic with pay attention, because this topic is very important for higher study. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.